Hello and welcome to Virtual Summit 2020 Cloud Storage Strategies. In this session, we'll discuss various storage strategies, performance, and cost when it comes to your InterSystems Iris-based deployments. My name is Mark Belinsky. I'm the principal technology architect here at InterSystems. I've been at InterSystems for 20 years and have spent the majority of my career in system architecture, deployment, and design. During this session, we'll cover three main areas about cloud storage. We'll start with a quick review of different storage types, then jump into how storage performance can be significantly impacted by the deployment design itself, and then wrap up with some cost comparisons and the implications of those. From this session, I hope you come away with the understanding of how the different storage types within your system's products, how to design your deployment for optimal storage performance, and finally, some ideas on how to minimize cloud storage costs, because if left unchecked, storage costs can become significant. So let's begin with a review of the different storage strategies. With any of the cloud providers, storage is essentially available in three flavors. You have block or disk, file, object, and then local SSDs. And with these four types, there are inherent limits and throttles. These limits can be increased in some cases, and in some cases you cannot. I provided three URLs here for quick reference to the three major cloud providers' storage portfolio. We have Google, AWS, and Azure, and so hopefully they come through on the slides. To quickly cover each of the storage types, there is block or disk. This is the most commonly used storage type within InterSystems product-based deployment. Block storage is for the Iris installation itself, configuration files, database.dat files, and journal files. And that's both the write image journal or WIDG and the transaction journals. Typically, block and storage will have the fastest performance of all the persistent storage types in the cloud, and ideal for small block random IOs, which are used in Iris itself. File storage is a relatively new storage type, maybe been around for a few years, and is great for sequential access and shared folders between multiple systems, such as static files for a pool of web servers, data extracts or import directories, and even our online backup target locations. Storage is persisted to your VM or compute instance as an NFS, a CIFS, or a SOMB amount. Then we have object storage, which is probably one of the original cloud storage types. It is not mounted as a file system, but rather access is programmatic through your application or operating system by the cloud provider's SDK methods or some APIs. Last but not least is local storage. And this is an interesting option in that it typically provides the fastest performance, especially with the addition of NVMe SSD drives with ultra low latency in the microseconds, and up to several terabytes of capacity. The storage is used as a block or a disk device in that it can be mounted as a file system to the operating system. The major drawback to this type of storage is that it's ephemeral, meaning it's only persistent for the instantiation of the OS runtime boot. On instance restart or reboot, the storage is reinitialized and the data is actually gone. So you want to be careful on how you use those types of storage. Plans are underway for InterSystems Iris to start leveraging object storage either in an automated fashion or allowing direct API access from within Iris object script or class methods, and also looking at local NVMe SSDs for potential use cases as well. So stay tuned for new details as they emerge. Earlier in the session, I mentioned storage limits. There are numerous limits to be aware of, such as the number of disks per instance, IOPS and megabytes per second for each disk device, IOPS and megabytes per compute instance type, and even IOPS and megabyte limits on your entire cloud account or your subscription. There are, as I mentioned, limits on the number of disks you can present to a single instance or VM, and at the total size for each of those disks. So limits are everywhere to be mindful of. There are several methods in dealing with these limits, and I'll cover those in a little bit. So, what happens when a storage performance limit is actually reached? There are two specific effects of I/O throttling, those being latency and throughput. Latency is the speed in which a single I/O is completed, and throughput is the total number of I/O operations you can do, or the amount of bytes or kilobytes or megabytes in a measurement of time, usually in per second measurements. So when reaching an IOPS limit, the cloud provider will induce latency at their hypervisor or the storage layer. So let's say you have an application that has numerous concurrent processes trying to do a total of 5,000 IOPS collectively, but you have a limit of only 3,000 IOPS because of your defined disk type or size. The cloud provider will increase latency on each I/O operation so that the aggregate of all the IOs that are called do not exceed that 3,000 IOPS limit. To demonstrate this a bit more, I have an example here using our RAN-read utility, which is available on our developer community website to easily demonstrate IOPS throughput, latency, and what happens when we reach a limit. In this example, I have a 500 gigabyte database residing on a single 800 gigabyte EBS GP2 or general purpose disk volume. AWS limits imposed on any device is 3 IOPS per 1 gigabyte of deployed storage with a minimum of 100 IOPS. However, for these EBS volumes less than 1 terabyte, they can potentially allow you to burst up to 3,000 IOPS. Just on a side note, EBS volumes have a total maximum of 16,000 IOPS. You can also choose either an IO1 or the newest IO2 EBS types, which are provisioned IOPS volumes that are great for smaller volume sizes, but that's a little different, and I'll cover that in a few moments. So in this example here, I used RAN-read at numerous job levels and ran the same job level multiple times just to make sure the results don't skew or there's wobble from run to run. I started at 2 jobs, and that sustained about 3,600 IOPS. And again, each IO here is an 8K database block read from the iris.dat file. And I'm able to achieve this because of the AWS allowing this bursting capability beyond the calculated 2,400 IOPS that I should have only been able to get using that same 3 IOPS per 1 gigabyte formula. And as I started more and more jobs, I started with 2, went to 4, 8, and then 16. We see on the blue line here in the graph that the IOs actually plateau just above 3,000 per second, and we see latency is negatively impacted as the number of jobs increased. We started on the left at approximately, call it maybe 1 millisecond, and then as more jobs are added, IOPS remain flat, and latency of each process suffers in that it slows down the I/O speed of each individual process. So we can see here there's a very clear plateau, and as we approach that response time utilization curve, we see that our utilization or our total throughput remains the same, but the latency starts to increase as we try to push more and more through it. So we covered an example of how cloud storage limits are quickly reached. So now let's discuss how to work around or account for these types of limits. As I mentioned previously, the size of the volume dictates the I/O rate for each individual disk device. Each cloud provider does this a little differently, but for the most part, the concepts are the same. Additionally, there are options to deploy provisioned IOPS. These are useful for scenarios where you have a very small storage space footprint, but you need a high I/O rate. Examples, again, are AWS EBS IO1 and the new IO2 volume types, where you define not only the size of the volume, but the desired I/O rates. And the meter's running on those in that you then pay for not only just the space, but also the IOPS that you want to provision. So how to work around these limits? There are 4 options available. First, consider a storage optimized instance if you are needing to do tens of thousands of IOPS in a single instance, or if you're running on a really, really small instance type, say, for example, one of the T3 or small M5, M5 large or M5 extra large, those will have imposed limits. So you may need to increase your your instance size just to achieve more IOPS. Second, you can just simply use a larger disk. if your instance type is already large enough to accommodate the total IOPS. By doing this, you gain more IOPS, again, because using that 3 IOPS per gigabyte rule, but at the cost you're paying for more disk space. The third one is use multiple disks grouped together using LVM PE striping or physical extent striping. I'll cover this one more in more detail in a little bit. And then fourth, using local engine storage. But please, again, there are risks when using this, and steps need to be taken to offload data to other persistent storage types periodically, either in some sort of automated fashion. If you need that data to be available after an instance restart. Expanding a little bit more on these options. So option 1, again, simply increase the size of the EBS volume. For example, if an IOPS target is 5,000, the EBS volume needs to grow to approximately 1.6 terabyte to achieve that. So it's easy peasy. But now we're paying for 2 times the storage capacity. This might not be a bad thing, especially in the long run, where your database grows rapidly over time. So if you're looking at adding that much capacity throughout a short number of months, it's really a non-issue. But if your database doesn't grow that much in a year, then you have to pay the penalty for it, basically. Option 2 is the LVM PE stripe I mentioned earlier. And what this does is it allows spreading the single iris.dat file across multiple disk devices. This has 2 benefits. You can retain the 800 gigabyte total disk space, but instead of 1 800 gigabyte volume, you have 2 400 gigabytes at each size. So your storage cost is actually the same, but this allows you to effectively double the IOPS capacity, assuming, and again, this is important, assuming the 3,000 bursting IOPS capability is available and taking advantage of it. I'll show you an example of this model in a little bit. Just a quick overview of the benefit of PE striping and LVM, or Logical Volume Manager, in Linux using a physical extent, or what's known as a PE, as its underlying structure, at least one of the underlying structures. Effectively, LVM PE striping places an individual PE, or a chunk, on each disk that you have allocated to the volume group during the logical volume creation, and then circles back in a round-robin fashion. So here in the picture, I have a simple 4-disk volume group. I create an LVM stripe for my logical volume and 4 megabyte physical extent size. This will place 4 megabytes of my logical volume or file system on each of the 4 disks. The size of the PE is configurable, and most often used is a 4 megabyte or even a 16 megabyte extent size. Me personally, I like using a 4 megabyte, but it's my personal preference just to reduce the chances of a hotspot on disk. If you have questions about LVM PE striping in general, please contact me and I'd be happy to go into further details. To recap the initial run we did on the previous slides in a single EBS volume, ran peaked at just over 3,000 IOPS as we scaled beyond 2 processes. Now, using a 2-volume LVM PE stripe, we doubled the throughput, as seen here in the middle graph, to 6,000 IOPS while sustaining the same level of latency and at the same cost of the single 800 gigabyte volume size, since there were only 2 400 gigabyte volumes. As the graph shows, once the limit threshold is reached, the IOPS plateau and then more jobs are added. Latency for each process increases accordingly, and essentially the IO limit is reached. Now, using the same 4 LVM PE stripe, we quadrupled the throughput from the original 12,000 to 12,000 IOPS while sustaining the same level of latency. This is using larger devices as AWS starts to get wise about bursting, and IOPS and latency gets a little choppy. This is a good model for growth, as you can expect each EBS volume and get more IOPS and space capacity when needed. As the graph shows, once the limit threshold is reached, again, the IO is plateaued. Then as more jobs are added, latency for each process again increases in corresponding fashion and sacrifices individual process performance to maintain the total aggregate throughput limit. So far we discussed the different storage types, storage volume limits, and how to design around those limits. So let's discuss the cost implications of the various storage types. Here we have the 3 persistent storage types. I don't have local storage here because, again, it's an ephemeral storage and not truly persistent, at least persistent, not beyond a reboot. Starting with block storage, we can categorize this as the best performance for transactional workloads that require low latency. I would consider the relative cost moderate, but typically the most storage used in an Iris deployment, so it can be considered actually a high cost just because of the amount of storage that you have to have allocated. File storage has fair performance, and it's a bit higher latency profile compared to block storage. File storage also has the highest cost per gigabyte compared to other storage types. However, there's usually less total gigabytes allocated, so the overall cost is actually lower, or consider it moderate. Object storage has fair performance, and that's subjective as to whether it's fair, poor, or good, and certainly has higher latency and geared more towards a throughput model. One of the drawbacks here is there is no direct access method from within Iris today as of yet. You'll need to programmatically use that using the cloud providers, SDK, or APIs. However, we're looking into support an API method directly within Iris and possibly other automated methods for the core system components of Iris itself. So again, stay tuned on that. So here we have a quick comparison showing the 3 persistent storage types, allocating 2 terabytes of capacity in each. Starting from the left, 2 terabytes of EBS GP2 storage is about $200 a month. Then EFS for file storage is a whopping $600 a month. And then finally, S3 for object storage is only a tiny $46 a month. Now, S3 has other potential price kickers in terms of access patterns to get for get and post transactions to access your data or put new data out there. So the pricing will vary a bit if you access the S3 buckets often. However, it's still very low cost considering. I don't have the longer term or archival options such as S3 Glacier, which also has variants within it, but those have even lower price points than the traditional S3. For these prices, I use the AWS Online Calculator and specified US East as my deployment region, and the pricing calculator can be found here in the URL at the bottom. One quick final topic I'd like to cover, and that's third-party storage appliances and management options. These options are gaining in market share and certainly features. The benefits here allow for adopting hybrid cloud solutions or simply carrying over storage management features you might be accustomed to with on-prem SAN storage, such as deduplication, compression, replication, automated tiering, and certainly even better performance, lower storage costs, and or both. And I'll explain that in a little bit, how we can potentially lower the cost. It gets you into support these third-party products, get into supporting a more, I'll call it an enterprise-grade storage solution by also offering cloning and snapshot capabilities. Sure, these cloud providers have snapshot capabilities, but it's not quite as mature or feature-rich as you currently see with on-prem storage solutions. So these third-party solutions leverage the same cloud storage types for the actual storage units underneath it, but it layers on intelligence, data reduction technologies, performance enhancements, and so on. Of course, these enterprise solutions are not free. There's definitely a threshold where it becomes cost-effective and actually lowers your storage requirements, total cost of ownership. 2 examples we provided here, NetApp Cloud Volumes on Tap, or CVO, and Pure Storage's Cloud Block Storage, or CBS. You can certainly reach out to these vendors for further details and exploration, and the InterSystems technology architects are here to certainly help with discussions around these appliances. So to wrap up our session, I'd like to leave you with 3 key takeaways. Usage. Using the right storage type in the right situation is really key for providing you the best environment for your InterSystems-based deployments. Performance. There's limits everywhere, and there are a lot of strategies and methods to design around them. And cost, understanding the balance between cost, performance, and the different strategies to make for not only a cost-effective storage model, but also still performant. For the next steps, I'd like to invite you all to my next session on cloud backup strategies, and certainly visit our learning services at learning.intersystems.com for a large array of documentation, training, and instructional material that's available. Please do stay in contact with me. You can reach me via email at belinsky@intersystems.com or via my LinkedIn page as well. And with that, I thank you for attending my session.